All right. Actually going? Yes, we're actually going. Okay. So, hello, friends, family, and random internet strangers. Welcome to week number 6 of working our way through code. So, first chapter I had you read this week is a little bit trippy because we start sending signals back into themselves, or the output of circuits becomes the input of the same circuit, and it gets a little funny. So working through explaining it is going to be tricky too, because I tried to build a couple things, but they either didn't work right or they were moving so fast that it's not really worth showing off. If I try and run them through our simulator program, some of them just flat out refuse to run. Like, it detects that there's an oscillation loop in the circuit and just says, nope, I'm not even going to try. Or it completely freaks out and makes the entire circuit just not work correctly. So I'm going to sit and kind of try and draw some stuff and re-explain some things, and you can ask me questions and hopefully it will make sense. There's my pen. So we started with the simple, like, talking about making a buzzer out of a relay, basically. So we have our relay with the outputs, levery doohickey there. Then we have our lovely coil of wire going here. So this, you are battery, connect into there, and this through a switch into here. Okay, so this is where we started with. So the idea is when you, oops, when you close the switch, when you actually make this connection, this guy goes, the lever inside the relay ends up going up because we've now completed this circuit, right? But because this circuit is now completed, how do you say that better? The circuit ends up dropping itself out because somewhere, hold on. Did I draw that right? Try that again. I think I did something off there. Okay. Oh. Battery. Okay. Oh yes, I did do something backwards. Right. So yep, because this should be connected there. It should there. Gets pulled down, not pulled up. Okay, there we go. That's where I screwed up. So that goes there. Goes here. Comes out here. the switch. Okay, so when the switch isn't pressed, the circuit gets broken up here, but when we go and actually press the switch and complete this circuit, power flows through here, which then turns the magnet on and then pulls the lever inside the relay down, which then turns the switch off. So it breaks the circuit over here, right? Because the magnet's on now, so this gets pulled down, so this gets turned off, which then brings the lever back up and recompletes the circuit, so it turns on again, which pulls the lever down, which breaks the circuit, which turns the thing back on, and over and over and over again, it just sits and loops around and around and around, turning itself on and off and on and off and on and off until, you know, the battery dies or the universe explodes or one or the other, right? So does that kind of make sense? Yes? Cool. All right, so this is one way, anyway, that we will tell a computer to do something over and over and over again, or like do something on a regular basis. So this will become very important in about 2 weeks. So the other thing, or the next piece of circuitry that we looked at that uses this whole feedback concept is what we called a flip-flop, or basically a 1-bit piece of memory. So we started with 2 NOR gates connected together. NOR gate number 1. We also had 2 switches, which I'm just going to represent with little buttons for now. So that feeds in there. Feeds into another one here. This one there. There. Good. Okay, so normally this thing starts off, because again, these are NOR gates, and if we go back a couple weeks to when we talked about all of the basic logical functions, remember that one. So not or. So normally it's an or. So that's a 0. That's a 1. That's a 1. That's a 1. So if we have a NOR, we have not that. So here, which means under normal circumstances, when nothing is pressed, this line right here is on, right? Because this input are both false. They're off. So the other output eraser stays off. Okay. Wrong one. Let me go there. There. All right. So when we press this button, that was supposed to be. When we press this button, or we close this switch, this input turns on, which turns this input off, right? because now one of these things is on. So this turns off, which means this is now a 0. This is also a 0. So this becomes a 1. So this turns on and turns this thing on. So now, even when I let go of the button and this turns off, this green line up here on the top is still turned on, which means this line here in the middle also stays turned off, which means it's still a 0. And the other thing's still a 0, which means the output stays a 1. And we keep this feedback loop going so it stays turned on, right? So next, when I hit this button, this goes, turns on. This now becomes a 1, still a 0. So this becomes a 0. And this all turns off, right? Which now means, because this is a 0 and that's a 0, this now becomes a 1, and this turns back on. This becomes a 1. This doesn't really matter at this point whether we're still pushing the button or not, because since this is a 1, this turns back into a 0, which keeps this whole top part turned off until we go hit the top button again and repeat the cycle. So, does that part make sense? I'm getting thumbs up and affirmative head shakes, so that's probably a good sign. Okay. So this is again, the basic flip-flop circuit. So we can remember a single bit. What's the next step with that? So we have that. And instead of having the two buttons to either set or reset, so that's why we also call this an RS flip-flop or an RS latch, because we have a set and a reset, or a set and a clear button or switch or input or whatever you want to call it. Figure all this out. This one's going to be real fun to try and draw by hand. All right. So I'm going to skip ahead in the book just here. So we're going to make a different circuit. We talked about this one's called the D-type flip-flop, where we have a data and another input that says, okay, remember whatever the data is right now. So we keep the same basic RS latch structure in here, although I'm going to draw it a little bit differently this time. So we have NOR gate here. NOR gate here. Probably this one. Here. This one. Over here. R2. So this would normally be like the set and the reset from before. But now I'm going to throw a couple of AND gates on top of it. So AND gate here, here, And I'm going to call this, the book calls it the hold that bit input, because this is the thing that actually makes it remember whatever's coming in. So I'm just going to label it H, call it a button. Good. So that is in here. We also have a data input, which gets fed an inverter up here. Okay. So when the hold that bit, when the remember thing is turned on, which also, because the data is not turned on, this gets turned on. Also, if I do it that way, I should probably flip those because we're doing it. Oops. Like that, that becomes the reset side, this becomes the set side. So my data input is 0, my hold that bit input is 1. So because both of these things up here on top are true, this line turns on. Again, this turns off because both of these inputs here started off as 0. This input turns on. That means this all turns on. And because either one of these are on, this whole side stays off, right? So let's see what happens when we turn this on. So this turns on, which means this part all turns off, which again, that's an and. One of the inputs turned off, so this turns off. Put this one down here, because now both of the inputs down here are on. This one turns on. Okay. So, because one of these inputs is now turned on, this all turns off. And now, because both of the inputs to this top NOR gate are on, this part turns on. Okay, so now even when we let go of the data button and these turn off, which means this turns off, we still have this line up here that's turned on, which keeps this this guy down here turned off, which then keeps this one up here turned on, which then keeps this guy turned off, and we get into this whole feedback loop again, right? So, does that make sense? Okay. So, you can also see that when we turn the H, or we let go of the H switch, so we stop remembering what's going on. Because that turns off both of these AND gates, no matter what the D input is, right? Because AND gates, one of the things is off, so the output's off. So that means our original RS latch circuit just sits and maintains whatever steady, stable state it was already in. Because, again, we've effectively turned off the first half of the circuit. All right. Questions, concerns, things I can clarify, further explain? No? Great. Moving on. So, it came next. Okay. So, this part, we actually kind of can simulate a little bit because at this point, we don't really care about sort of the guts of how the counter works or how the memory works. We just want to see it actually, do its thing. So we can't necessarily build all of the components from scratch in Logisim, but it has components that do the same thing for us that, don't make the program crash or do bad things. So we can actually demonstrate here real quick before we get into the meat of it. So I just drew an SR flip-flop, right? Or that was the thing we started with, really. So I'm going to go grab a couple of buttons and an LED to watch this thing. And I think so. This is actually working like the second thing we did, where it has the, call it the hold that bit input, or the clock input, as we'll later come to refer to it. So I can now set and reset my memory, and it doesn't matter what state any of the inputs are, it's still going to remember that last thing that we put in while our hold that bit input was turned on. So if you put a bunch of those together, the book calls it an 8-bit latch, where it takes 8 bits of input, has again the clock or the hold that bit input, and has 8 bits of output coming out that tell you the last thing that it remembered. This also has the same thing, except it calls it a register for reasons that we will find out in a couple weeks. So this lets us take in however many bits we want. On this D input up here, we have the write enable, which is basically whether it will actually save things that are coming in or not. And then again, we have our clock or hold that bit input down here. We have our Q output coming out up here. So wire this up quick. We always want it to write. Got is, so here's my 8 bits of input that I'm going to set up to take 8 bits in, and stick that on there, wire that into my input, and there. The other nice thing about this is it's got this little number on top that will show you the value that it remembered. So we can actually look and see what each individual little memory cell is currently holding, which if you actually wanted to sit and follow along with the book and put together a real computer with all of this, is going to come in super handy. So up here, I put this together earlier. This is basically the remembering adding machine out of the book with a couple little extras. So in order to save some time in copying and pasting, Logisim actually has a out-of-the-box adder circuit like we built last time that I used because I didn't want to have to, remake everything. So that's what this is. So we've got one dip switch wired into this input, another dip switch up here running through what the book called a 2-to-1 selector. Logisim calls it a multiplexer, a slightly more general term. Yeah, anyway. So this lets us pick whether we want to have our input from this bank of switches up here or from our register that we have stored up here and feed that into the other input of the adder. Adder's output goes to both the array of LEDs like we saw last week. I also have it going into these hexadecimal digit display thingies up here, and then wired back into the D input for our 8-bit latch or register up here. I also have a save button wired into. So if right now, I want this turned on, so it's grabbing the switches. Let's say I want to add 1 plus 1. That gives us 2, which I can then save into my memory up here. I'm going to turn this off, so we're now adding to memory. And I'm going to hit this. I'm going to say whatever's in the memory plus 2. So I have now built a simple calculator that can also count by 2s. So, does that make sense? Yes? No? Probably? Okay. So, this right here, technically, in the most strict academic definition, we've now built a computer. Because we have input, we have processing, we have memory or storage, and we have output. This is not exactly what I'd call a general purpose computer because it can literally only sit there and add numbers together. But hey, it's a start. Next thing the book gets into, which I'm not even going to try and draw and explain and make it all work, is a latch that is triggered. I can actually go see this here because I'm not going to draw the whole thing out, but it will actually simulate it nicely. Is what's called an edge triggered flip-flop instead of a level triggered flip-flop. So what that means is instead of our clock having to be on for it to go, it's going to go whenever the clock signal changes, whether it's going up or down in theory. Although I think this one is actually only built to go when the clock goes up, not necessarily when it stays up or goes down. So we can see that. I'm actually copy and paste. It's lazy. So if we grab one of these. Oh yeah, that's right. This will only work with these, which will do the same thing. That, turn my right enable on. grab a second here. All right, so let's go put some stuff in here. Okay, so I've made this a positive transition. It is now positively transitioned. I can turn this stuff off and it's still stuck. It still says 34. Except when I transitioned again, it picked up the 0 because now this is 0. So I'm going to go put some stuff back in. Whoa. My switch on. I think the simulator's freaking out a little bit. Yeah, I think it's not updating my switch when I switch it. I may have found a bug in the program. Anyway. So when I switch the switch, it doesn't matter whether I'm going up or down, the thing remembers. And I can change my input even while the clock control is turned on. I can change what my value is, and the value in the memory still doesn't change because this is only watching for transitions, not the actual value that's on the line. So, does that make sense? Yes? Cool. So, last piece of this is, again, not even going to try to draw this one, the called the like counter divider, frequency divider, and the counter circuit that lets you string a couple of these circuits that are oscillating back and forth together so that they oscillate over longer periods of time and end up, if you put them together correctly, basically counting in binary from 0 up to however many bits you have in your counter. Again, not really gonna try and draw that, but oh, hello. That's a much more complicated piece of circuitry than I was hoping for. I saw the thing had a counter. I didn't actually play with it beforehand, so. But we also have a much more approachable, easier to understand in the context that we're looking at counter over here, right? Because I can clear this out, add 1 to it all the time, and I get a counter. So that's about it for chapter 14. Any questions? Did I do a better job? Oh, I see a question incoming.
The Q and the Q bar.
Mm-hmm.
So where is that on here?
So,
okay.
The Q is just our output of what we've remembered inside of a circuit usually. And then Q bar is basically not Q. Usually anything with a bar over it just means not whatever it is. Okay. So this particular component doesn't have an actual Q bar output on it. I think. Yeah, this guy does, although it's not labeled. But we can kind of see it has this little bubble off of the end of this other output down here, which usually means not. And hey, look, even the tooltip says complement of current flip-flop state. So it's whatever the opposite of this is. So it's something you use sometimes, and sometimes you just kind of ignore it.
Okay.
Any other questions? Okay. So we'll see all of that again next week when we start putting a bunch of these latches together and putting groups of them together and putting the groups of them together and actually getting larger amounts of memory that are slightly more useful. chapter 15, we've mostly already talked about because we've showed you hexadecimal counting before. If you want a little more practice with that, that's actually why I added the hexadecimal output up here to my calculator circuit, because now, again, if we start counting, it will actually count in hexadecimal for you. And if you want to sit and do the math to convert, okay, 16 in hexadecimal is 16 plus 4 plus 2 is 22 in decimal, regular people counting. You can sit and play with that if you want to. Again, I will post this file to the website when I go upload the video here in a little bit. So unless we have any more questions, I think that's about all we've got for this week. No? All right. So next week, again, I think read the next 2 chapters. We'll talk about memory and starting to build an actual programmable computer, not just one that sits here and does one thing over and over and over again. So see you all next week.